Hello. Well, I'm happy to introduce Dr. Lanqiang. He has been working with the optics department since February 2019, and today he's going to give a presentation about progress on solar multi-conjugate adaptive optics in China. You can start. Thank you.
Okay. Okay. Thanks, Ugo. Thanks for giving me the opportunity to stand here. Okay, good morning, everyone. I'm Zhang Lanqiang, if in Chinese order. I'm Zhang Lanqiang from China, and now I'm working here as a postdoctor for the project of the European Solar Telescope. Today, I'd like to give a presentation about the progress on the multi-conjugate adaptive optics in China, which is the main study before I come here. In China, I worked in this institute. I'm not sure you know this, the Institute of Optics and Electronics. It belongs to the Chinese Academy of Science, and it has there is a key laboratory on adaptive optics in this institute, and this is the only one, I think, the only one key laboratory in China for the specific research on adaptive optics. And here there are more than 120 staff worked for adaptive optics in different application fields. The reason I said the progress in China, but not the progress in this institute, because I'm not sure some of you know this institute. Actually, this institute is the only one in China with the essential progress about the multi-conjugate adaptive optics. Okay. Okay. Today I'd like to give the talk in these three parts. First, I will just introduce the multi-conjugate adaptive optics. Normally we call it MCAO for short, for the solar observation, and I will just introduce the MCAO and solar observation. They need each other, and I will just explain why in this part. And after that, I will give a short introduction about the development of MCAO in this institute, in the IOE. And then at last, I will finish my talk with a short summary and the future plans. Okay? And when I started my PhD, let me see, 12 years ago, I was taught that was quite important to observe the solar surface with high resolution. Although nobody told me why it's quite important. None of us studied the solar physics, because we are engineers. Anyway, I got my start point for my PhD, and tried to do something for this topic. And normally we will use the adaptive optics for the ground-based telescope if we want to get some high-resolution image to just detect and compensate the turbulence influence from the turbulence. This is the principle of conventional adaptive optics. It will just test and detect and compensate the turbulence distortion from one direction and to get the high resolution image. But from this, we can find that there's some limitation for the conventional adaptive optics. We'll see that if the sunlight from the other direction, they will not be well compensated because some information lost in the high altitude. That means the correction field of view normally would be quite small, and because for this part, just like some wavefront error come from this part will not be compensated. This is what we call atmosphere and isoplanetism, and normally the correction field of view is less than 10 arcsecond invisible. I think it's not enough for the solar observation because the typical solar active region is more or less 1 to 2 arc minutes. That means we need some new strategy for this problem. That is multi-conjugate adaptive optics. Okay, and here consider that there are turbulence in different altitude, just like the different turbulence layer. We can set several deformable mirrors at the conjugate place of this turbulence layer and compensate it one by one. After that, we can get the diffraction limited image in the large field of view, more or less like this. And on the other hand, of course, from this principle of MCO, we can find that it needs several guide stars and more different mirrors. And it means this technology would be much complicated compared with the conventional AO system. This is an example that observed result from the MCAO system at the Goody Solar Telescope in America, actually in Big Bear Solar Observatory. Here we can find the effect of MCO directly, because compared with the conventional AO system, the MCO from the MCO correction could get more or less even large high resolution image. Actually, there is another high resolution imaging technology in with large field of view, that is the ground layer adaptive optics. From my point of view, I think it is a byproduct of MCO, because most turbulence, as we from our observation, we find that most turbulence was distributed on the ground layer. If we just focus on this ground layer turbulence and correct it, we can get the high resolution image in even large field of view. But of course, we cannot get to the diffraction limit image because of the high altitude turbulence. It's just like this. And in some institute or in some research group, they just studied the ground layer adaptive optics as the first step for study the MCO. Okay, let's go back for the MCO. Here I just list the main progress of MCO, including the theory research and the system experiment. We can get that maybe up to 2000, several experiment system was built based on solar telescope and the nighttime telescope. And this lines with the red box is some experiment on solar telescope. Okay. As I said, the solar observation need MCO, and actually I think MCO experiment also need solar observation, because compared with the nighttime observation, it would be quite easier to take some MCO experiment on solar telescope. As I introduced before, MCO need several guide stars or regions for the waveform sensing. That means for nighttime telescope, we have to develop the multiple laser guide stars, or we have to find the several bright stars as a guide star in a certain region. It would be a bit difficult. But for solar observation, we can adopt the structure on the solar surface freely as we want, just used as the guide region, such as the sunspot or granulation. That's why I think almost all the main solar telescope take some experiment on MCO around the world. Here I just list the main telescope and their experiment MCO system. And among them, 2 telescopes are here, in Tenerife, in Teide Observatory. The 0.7 meters Wellcome Tower telescope and the 1.5 meters Grigor telescope. And the other 2 in America, and the last one is in China. And The research group in Europe, actually, I think maybe many of them from Germany, they studied to develop the MCO on the Vaucluse telescope, the VTT, and it also, this experiment system is the first one to get the on-sky observed result in 2003. For this experiment system, they just added a higher altitude correction behind the correction adaptive optics, so that it's quite easy to take the experiment. And the turbulence would be corrected in 2 layers. They just added another different mirror, and meanwhile applied a new large field wavefront sensor with the field of view more or less 14 arcsecond. From the result here, we can find that the image improved a bit in the large field of view after MCO correction. Almost at the same time, there is another group in America. They just developed the MCO based on the Dawn Solar Telescope, DST. And they also tried to use 2 different mirrors and one wide field wavefront sensor to take the MCO experiment. But as I know, I'm not sure this system worked quite successfully, because no more information, especially no more observed information came out from this system. And actually, up to 2010, no more information about this. After this first generation research for these 2 groups, they tried to build the new MCO system for their new telescope. In Europe, we have a new telescope of Grigor Solar Telescope, and I think it started to observation maybe 212 or 13 sometimes. And they tried to build a new MCO system for Grigor, which tried to employ 3 different mirrors, and one on-axis wavefront sensor and a multiple direction wavefront sensor, or the wide field wavefront sensor. This is some result from the Grigor MCO experiment system. Also, for this system, there's no more information published after 2013. Maybe some of you know more about than me about this system. As I know, both of the European and American team worked together to develop a new MCO system for the Goody Solar Telescope at the Big Bear Solar Observatory. Actually, they built several wavefront sensors to test the different configuration of MCO, and at last, they decided to use one multiple direction wavefront sensor and to control the 3 different mirrors for the turbulence correction. Here is the last observed result. I think this system is the one that is most close for the regular operation, because now it can close loop for more or less 1 hour stably. Besides this experiment system, also here, in IC, we are developing an MCO bench for the EST, for the European Solar Telescope. We try to use 2 wavefront sensors and 5 different mirrors. I think this is the most complicated one in the world for developing. Okay, this is some development about MCO for solar observation. As I said, solar observation need high resolution image in large field of view. On the other hand, it's quite easy to take some MCO experiment on solar telescope. And after that, I'd like to give some introduction about the MCO development in China, actually in the IOE. The study of solar adaptive optics in the IOE started from 20 years ago, more or less. And they built the first tip tilt correction system in China in 2001. After that, from more or less 2010, based on the new Vaucluse Solar Telescope, NVST for short, we call it. We developed two-generation solar adaptive optical system and some large field adaptive optical experiment system as well. Meanwhile, they tried to build the largest solar telescope in China, the 1.8 Chinese large solar telescope, CLST. Here, just give the main parameters of the two-generation adaptive optical system on NVST. One thing that was mentioned is, as I know, this system, I mean the second generation adaptive optical system, is still the fastest system, I mean with the wavefront sensing, 3,500 Hertz. Besides the development of solar adaptive opticals, they also just did some experiment on large field observation. First, they built a multiple direction wavefront sensor with 37 subapertures, and the field of view is 1 arc minute. Based on this wavefront sensor, they test the ground layer adaptive opticals first, using the different mirror as it was worked for the second generation adaptive opticals. This is some observed result. They logged the generation and make the GL system correction, GLAO correction, just like this. And after that, this is if we just combine the GLO and the speckle together, we find we can get the excellent image, just like we got the one of the most high resolution image we got. This is the open image. Oh, sorry. This is the GLO correction image, and this is GLO with speckle. Also, here is some videos for this. I think maybe GLO is another option for solar observation in future, because MCO is quite complicated, and GLO, if we don't need very high temporal spatial. Sorry about that. Temporal symbol, just like very high time resolution, we can use GLO correction plus speckle. Meanwhile, we did some research on the theory of MCO, and based on the simulation result I did before, we found that the correction result is not quite uniform with the conventional MCO configuration. So we proposed a new configuration that just GLO part plus a high altitude correction, like this. After that, we did some experiment in the lab, and 5 laser used for the multiple sources and 2 different mirrors we employed in the system for the turbulence correction. This is the result from the lab, and we can find, compared with the AO correction, the image quality improved in large field of view after M0 correction. After getting the result successfully in the lab, we tried to install this system on the NVST. And this is the layout of this experiment system. 2 layers. The first one, just 2 layers corresponding to the 2 lobes, ground layer correction lobe and the high altitude correction lobe, more or less like this. And the same parameters as it was worked in the lab. Here is the optical design, just got it. And here is the observed result based on NVST, the open lobe image, the ground layer adaptive optics correction, and the multi-conjugate adaptive optics correction. And we can find the image improvement. Furthermore, we just calculate the generalized Fred parameter to judge the image quality. Normally, we use the Fred parameter to estimate the turbulence the strength of turbulence. But here, we just calculate the generalized Fred parameter based on the spectral technology. And we can judge the image quality with the number of generalized Fred parameter. The bigger, the better. Compared with the open loop image, the image quality improved in the large field view after GAO correction, and even better after MCAO correction. Actually, we find here there are more or less 30 to 40 arcsecond field view. It's even better. That's because in our MCAO experiment, we just set the guide region. The largest field view for the guide region is 32 arcsecond, compared with the correction result. And we also calculate the contrast of the image to further confirm the effect of MCAO correction. The red dots are the contrast of image from MCAO correction, and the blue one is GAO correction, and the dark one is the open image. And we just adopt several areas to calculate and compare the result. We can find the result that from this result we can find that the performance for MCAO correction. Okay, this is the latest development before I'm leaving. I'm coming here. And in summary, I think after nearly 10 years development, we realized the MCAO correction with 2 different mirrors in the lab and on sky, and got the first light on NVST successfully in 2017. After that, a new MCAO system is under developing for the NVST as a routine instrument for science observation. And as I know, they try to demonstrate demonstrate this technology on NVST and after that we'll used it on the 1.8 Chinese large solar telescope. And this telescope just got its first light in December of last year. Here is some conceptual design for the new MCAO system on NVST. And we considered 3 correction modes: the unconventional adaptive optics, the ground layer adaptive optics, and the multi-conjugate adaptive optics. Another idea for this system is we try to measure the distribution of turbulence in real time, and based on this information to control and adjust the conjugate height of the different mirror, the high altitude different mirror, so that make the system can work in the optimized position or optimized situation. And last year, I know they just finished the detailed optical design and mechanical design. And maybe at the end of this year, they will do some on-sky test for this system. Okay, that's all. Many thanks for your attention. Thank you.
Question?
So you said that in the new design,
yes,
for the new telescope,
yeah,
you have the conventional adaptive optics option also.
yes,
So you will have the capability to change the wavefront sensor, just to go from conventional to ground layer? Or how will you switch from conventional to ground layer?
okay. Yeah. We try to put 2 wavefront sensors on the upper layer. One is the high order wavefront sensor for the correctional adaptive optic system, and the other one is a multiple direction wavefront sensor for ground layer and multiple conjugate as adaptive optic system. Actually, in this system, we will use 3 wavefront sensors for different correction modes.
So you will use simultaneously You will use simultaneously the high order waveform sensor and the
Yes.
multi-direction waveform sensor for the MCAO, for
Yes.
and for
No.
the ground layer also.
No, for down layer. These two waveform sensors just used for controlling the different mirror conjugate to a ground layer.
Yes. Okay.
And the other, in the down layer, there is another multiple direction waveform sensor, which we use to detect the turbulence aberration in higher altitude, and controlled another two different mirrors. And totally 3 different mirrors would be used in this system.
So thanks, Zhang, for your talk.
Thank you.
I have a question regarding the configuration that your proposal of decoupling the ground layer and the high altitude correction.
Mhm.
I think the results that you showed, no, the next slide.
Next.
Yes, that's the configuration. Okay,
Yeah.
that's the configuration. My question is, I guess that you have got best stability of the closed loop
Yeah.
with this configuration
Yes.
and a best correction. So I have two questions. The multi-directional waveform sensor that you use for the ground layer,
Yeah.
does it have the same field of view as the multi-directional waveform sensor of the high altitude correction, or maybe it can be of a shorter or a smaller field of view?
Yeah. Okay. And for this configuration, we will use here one. We will use two multiple direction waveform sensor. Actually, one is for ground layer adaptive optics, and the other one for high altitude correction. Actually, we thought that the turbulence for ground layer is much stronger than that on high layer. So for this wavefront sensor, we will use smaller field of view, but more subapertures for detecting the ground layer. But this one, we try to use the bigger wavefront field of view, but less subaperture.
For example, if you want to correct a total field of view of 60 arcseconds, for example,
Yes.
can you use a waveform sensor for high altitude correction of 60 arcseconds and for ground layer only of 20 arcseconds, for example, 20 or 30? Oh, ¿no se me escucha?
Okay, I understand what you mean. It just like work. It will work like as this configuration, just like the on-axis waveform sensor, just with a narrow field of view. But for this system, for this configuration, the uniformity of the correction result is not quite well, because you will find it would be much better in the center part, and after that, the correction result would be go down. The effect, if we just use this one as you suggest that in more or less 20 arcseconds, it will be appeared that problem.
It will be enough. 20 arcseconds will be enough.
Not enough.
Not enough.
Not enough. Actually, we tried as 24 arcseconds based on in our experiment for this closed loop, and we also find that that problem. Just like, yeah, for example, the correction, the image quality would be like this. In the center part, center field view, it would be better than the part in the board, on the board. So in the new system, we designed the multiple waveform sensor here as 40, let me see, maybe 42 arcsecond. And this one is 16 arcsecond.
And the next slide where you show the results comparing Strel of open ground layer and
This one?
I think the next slide. Oh,
Next
I'm
one.
not sure.
Okay, this one.
This one.
Okay.
These results have been obtained with with your proposal, the new proposal, the proposal of decoupled ground layer
Yes,
and high altitude.
yes, with the new configuration. But I have to say that yes or no. Sorry, because we didn't develop the two multiple direction wavefront sensor during this period. That is just for the experiment. After this, during this part, we just applied one different mirror. One wavefront sensor behind all different mirror. For the ground layer, we just make the different mirror conjugated to ground layer worked. And for the multi-conjugate adaptive optics, we just still use the wavefront sensor behind the two different mirror, but in the control process, we first just divide the ground layer information for the different mirror conjugate to ground layer, and then use the residual information control the high altitude. We didn't just based on the global tomography to control the two different mirror. Actually, we just first, for example, get the information from different side of line, average it, and use the average information controlled the different mirror one, and then after that use the residual wavefront information from each side line controlled the high altitude different mirror. Just make it work like this. It's not the real configuration actually, because we only have one multiple wavefront sensor. Okay.
Thank you again. Is it working? Okay.
Yes.
Thank you. Could you please the previous one? Could you please put this one?
Okay.
It looks you're showing the generalized Fried parameter, which seems to be a parameter regarding the turbulence of the atmosphere.
Yes.
So I wonder how can you explain to use such a parameter for measuring the quality of the correction, and eventually, I can see that the maximum that you provide is around 20 centimeters.
Yes.
Which is the I would say one of the standard parameters that we use in night time in our observatory. So there is something that I do not understand in this. So the question is, how can you use a parameter intended for measuring the turbulence, the atmospheric turbulence, in order to evaluate the quality of your results?
Okay. Thanks for the question, Luis. And from here, because as we all know, it's quite easy to estimate the system performance after AO correction in nighttime, because we can use the PSF, the stray ratio, this kind of things. But for the extended object, just like the solar image, we don't have this parameter to judge the performance. And actually here, the generalized Fried parameter, it comes from the speckle technology. For the speckle technology, we try to divide the area for reconstruction. But before that, how big the area? We should just estimate it by calculate we call it generalized Fried parameter. Parameter, because if the turbulence is weak, from the image we can get the bigger parameter, just like the generalized Fried parameter. Actually, it's not of my subject. I just don't know the general physics principle about this. And after that, if the turbulence is weak, we can get the higher value for this parameter and divide the image in big area so that we can just reconstruct it. And if the turbulence is stronger, that value, that parameter, the value of this parameter would be small, and we have to divide more area for reconstruction. And from this sort, we just use it to value the image quality. Just like if the resolution of the image is good, this generalized Fred parameter would be higher, would be bigger. It's just like this. But actually, I don't know how to calculate the Fred, the generalized Fred parameter in SPECO. I think it is one of some basic knowledge for SPECO image reconstruction.
How do you deal with pupil distortion on the wavefront sensor after the DM of high altitude?
I'm sorry.
How do you deal with the pupil distortion on the wavefront sensor after the high altitude DM?
Yeah. This is a question for all the MCO system. In our system, we also find the problem. Actually, till now we didn't solve this problem. As some suggested from the, I think the German team, they suggest just to reduce the pupil for getting the wavefront information after, if the wavefront sensor put behind the high altitude different mirror. But we just also find the problem. Now, till now we didn't test if this method could work or not. Just like because the distortion of high altitude different mirror, and it will influence the age subaperture for wavefront sensing. So most time we just omit the age around, the age subaperture around the wavefront sensor and get some information used for the wavefront correction. I'm not sure if I explained this for you. Okay. Thank you for coming.